Good evening, everyone. Welcome to the April 2021 meeting of the Naperville Astronomical Association. I'm Drew Carhart, the current club president. To start things off here, I'd just like to, as always, thank you for joining us, and happy that we're still getting to do outreach, give wonderful presentations like we have tonight via the wonders of the internet. And as far as before the program, I will cover briefly our upcoming events. We have just a few things on the schedule at the moment. 2 weeks from tonight, we have our Astronomy Fundamentals program series, and this month's presentation is on kind of an ancient art of telling where you are by looking at the stars or celestial navigation. And so if you are at all interested in how astronomy helps people explore our planet, this will be the place for you. And that's again 2 weeks from tonight, same venue you're at now here in our streaming lands. For May and our monthly meeting on the first Tuesday of May, which will be the 4th, we are having a guest presenter from the University of Chicago and the Fermi Institute there. And Dr. Caparilio is going to speak to us about what are generically called cosmic rays. They're not really rays, they're incredibly charged particles, and that people detected for the first times over 100 years ago, and scientists have been studying them ever since then, and we've learned a lot about where they come from along the way. So that will be our May regular meeting program. If you are not wanting to write things down as I speak here, the information is on our club calendar at naperastro.org. And as I'll always point out, if you follow us on Facebook, or if you're a member of the club and watch our message board, we'll note any other special events that we have coming up. We've been talking about this for months, and it's been a while since we've been out, partially the weather and partially other commitments and things that have kept us from doing some more astronomy observational streaming, but we hope to get back into that. And we'll sell our YouTube channel for those of you who are viewing us live tonight. If you go to YouTube and look us up, if you just search for Naperville Astronomical Association, or if you can remember, youtube.com/naperastro, we have all the programs that we've done over the past year pretty much there recorded. So if you missed something, and if you're watching us on YouTube right now, I'm obligated to say that we'd like you to subscribe, and then you will see future presentations pop up in your YouTube feed. This evening, as per usual, if you're watching us live on the first Tuesday in April, you can submit questions in the usual manners. If you're watching us on Facebook, just put them in the comments column, and we're monitoring that, and we'll pass them along to the speaker. If you prefer to ask questions via email, you can send them to us here at the address that's on your screen right now. Tonight's speakers actually have noted to us that they plan on answering questions at the end of the presentation rather than breaking along the way, but feel free to ask the questions as they pop into your head, and we'll keep track of them and pass them along to them at the conclusion of the meeting for them to, or the conclusion of the program for them to answer. So without further ado, this evening's presentation, we have a team presentation actually here. We're going to start out with our main speaker, who is Rhiannon Lau-Erskine, and she's an instructor at Wheaton College up the road from us here. And she helped manage a project with students this past summer, simulate settling on Mars, and they are going to give us a team presentation this evening. I'm going to let Rhiannon introduce her co-presenters when she gets started, but without further ado, I will turn the floor over to her.
Perfect. Thank you so much for the introduction, Drew, and for having myself and my teammates here this evening. We're thrilled to be with you. This is actually my second time speaking to Naperville Astronomical Association. I was with you about a year and a half ago, and I gave a very different type of presentation then than we will tonight. I was speaking on the research that I do with NASA, with their Meteoroid Environment Office a year and a half ago. But tonight we will take a very different tone, and actually the presentation itself is going to be told in storytelling form. And it's about a big project that myself and some students endeavored last summer. We entered a competition put on by the Mars Society to design a 1 million-person settlement on Mars. You may be familiar with these competitions. They're quite brilliant, actually, because they generate a ton of ideas for just relatively small cash prizes. And unfortunately, we did not win the competition, but we had a blast putting our design together. So we spent a couple months discussing different ideas and doing a lot of research, and we distilled that down into about a 20-page design. And then tonight, we have made it into presentation form for you all. So I'd like to start by introducing, or having my teammates introduce themselves. I have 3 brilliant students from Wheaton College's physics department with me tonight. So Rachel, do you want to introduce yourself?
Sure, I'm Rachel Barron. I'm a senior physics major at Wheaton.
I am Emma Henschel, and I'm a junior physics major at Wheaton College.
I'm Tamara Watson, and I'm a sophomore physics and education major at Wheaton.
Wonderful. And you may notice that we have a team name here. So we called ourselves Team Malacandra. And I'm assuming that many of you watching this evening are space nerds, much like ourselves. So you might know where this is from. But for those that don't, C.S. Lewis actually has a sci-fi trilogy that's commonly known as the Space Trilogy. And in those books, he calls Mars Malacandra. So that's where our name comes from. All right. So this project was thrilling on a few different levels, but one of the reasons why it was so exciting is because up until present day, technological limits have kept us from going to Mars. But soon that will not be the case, as both SpaceX and NASA are in the testing phases of rockets that will eventually bring humans to Mars. So you're probably quite familiar with SpaceX's Starship. The rocket on the right of this drawing here is the full Starship. SpaceX has been designing, and now they're actually testing this rocket. I think they've had 11 test flights so far. What they're testing is on the left here. It's a smaller prototype called Starhopper. So this is Elon Musk's goal to get to Mars. Just a little fun side fact about Elon Musk. I just noticed today that the Forbes billionaire list was released, and he's now the 2nd richest person in the world. So I think SpaceX is fairly well funded right now. The richest is Jeff Bezos, who also has a space company. So SpaceX will likely send their Starship to Mars within the decade. Likely first cargo ships, and then sending humans, and then eventually Elon Musk actually wants to create 40 cabins, to configure this so that it has 40 cabins, and so that he is able to bring up to 100 people per journey to Mars. So he has some very lofty goals. NASA is also very much in this race to Mars, though. They are building SLS, or their Space Launch System, and have been testing different components, such as their support boosters in the bottom frame here. NASA does have slightly different goals, though, in that they are first going to go back to the moon, hopefully put the next man and the first woman on the moon by 2024, and then they will set their sights to Mars after that. Mars has also been in the news a ton lately with Perseverance. So Perseverance is now, I think, in its 7th or 8th week on Mars's surface, just learning a ton about Jezero crater, sending back some beautiful images and using the various science equipment on it. So Mars is a very exciting place right now. So because this is soon going to be a reality, a human presence on Mars, the Mars Society in this competition asked us to think through all the different components of life on Mars. So obviously the most basic are technical questions, right? So about half of our presentation this evening will be on the technical aspects, on finding or figuring out how to get the oxygen, water, food, etc. that we would need to live on Mars. But there are also some really important social and cultural questions that arise when thinking about having permanent human presence on Mars. And questions of government, how involved will Earth be versus how independent will this settlement be? Questions of economics, again, how independent will they be versus dependent on Earth's economy, etc. So we are going to cover all those elements this evening. We'll present for about 45 minutes to an hour and then have a time of Q&A. But before we dive into this, I want to explain to you that we will present this design in the same way that we wrote our document. And that is from the perspective of settlers living on Mars in the year 2050. And we have organized this presentation in the same way that we organized the document. So what I want you to do is mentally go with us this evening for an hour to the year 2050, and the four of us are going to share our design from that perspective. So now that we have covered all of that, we will start with Emma giving the prologue.
December 2031. That's when we landed on the surface of Mars. There were only 12 of us at first, each selected from a different country, each a different area of expertise: engineering, agriculture, medicine, planetary geology, and more. All were united by the goal to put a city on Mars. The first colony on Mars was called A-XII. The name originates from Elon Musk's seventh son, A-XII. We changed the first letter X to M for our nation of Malacandra. This name is also where we get our nickname for the first 12 settlers, the Ash-12. Before the trip, they endured intense psychological and physical testing and training. All 12 were trained as astronauts and spent time at either the International Space Station or the Moon. After decades of planning, preparation, and training, the 12 explorers launched off Earth. 7 months later, they landed on Mars. They touched the surface on the eastern tip of Valles Marineris at negative 12.17 latitude and negative 38.94 longitude, a canyon 5 times longer and 4 times deeper than the Grand Canyon on Earth and the largest canyon in our solar system, picked not just for its breathtaking views, but for its strategic position on the surface as well. Without a thick atmosphere on Mars, the radiation is lethal on the surface, so the lower elevations in the canyon, as well as the sloped walls for building cave homes, provide necessary protection and a milder climate. Since there are not yet large bodies of water on the surface either, ample water can be found just beneath the surface of Mars, all around and underneath the canyon. At the tip of the canyon, where we're settling, water is only a couple meters away. A large cargo ship arrived at the crest of the canyon about 1 year before the first settlers. It carried drones, robots, and artificial intelligence designed to begin building the first colony and scouting out essential resources like water, minerals, and materials. The machines drilled deep into the surface to begin the tedious, time-consuming task of drilling that eventually built the tunnel system that is used in A-XII today for underground homes, buildings, and transportation between the different levels of the canyon wall. While most of Valles Marineris has sharp drop-offs and steep inclines, our eastern tip has more gradual elevation changes between a staircase-shaped terrain with 3 large steps, ideal for building above-ground structures one day. All of these factors were essential for the survival of the first colony on Mars. A-XII is a central location on Mars that is now the capital of our beautiful city, Malacandra. Humans were created with intelligence, curiosity, a sense of adventure, and a desire to pursue something greater. This has fueled our endeavor and brought a global unification. The 4 core values that Malacandra is built on and strives to maintain are: 1, life on Mars to strive for full self-sustainability, but also keeping connected to Earth. 2, as technology and culture grow and evolve, choice opportunities should abound, making life on Mars not scripted. 3, Mars should preserve the diversity of Earth while letting culture evolve freely on this new planet. And lastly, 4, Mars should be cared for and not exploited. This was inspired by the way that people on Earth took poor care of their own planet, and now we strive to instead preserve Mars' natural state as much as possible when building a city into it. All 4 of our core values are inspired by a Christian worldview. We understand that it is natural to fail and not meet these expectations. So we make sure to foster a culture of forgiveness and acceptance, followed by reparation to encourage healthy relationships, not just with others in our city, but within ourselves too. So far, with a short history of life on Mars, these values have strengthened our city. As you can see in this timeline of our history on Mars, we have some notable events, like Marcus Marineris, the first person born on Mars, so our first truly native Malacandran. Then about 10 years ago, in 2048, our government reached phase 2 in becoming a more formalized system. We are also planning to build a second precinct at the northern tip of the Tharsis Bulge, an impressive underground cave system west of Valles Marineris. However, our city plans don't stop here. We have plans for up to 10 total separate precincts all across Mars. When you first arrive at Mars, you might pass a space station orbiting our planet called Gateway M. Gateway M is the way that we will keep our cities connected. It will provide essential emergency transportation between the 10 precincts and carry equipment for hospitals and laboratories that are too heavy or expensive to ship. Our hometown, A-XII, is where we are streaming live from right now, the first official precinct on Mars. Like I mentioned earlier, we have construction plans in the next 10 years for the second precinct at the northern base of the Tharsis Bulge, one of the largest cave systems on Mars. We also plan on building another precinct at the other end of the cave system to connect the 2 ends of Tharsis Bulge through its underground tunnels and cave systems. The Lyot crater is going to be our northernmost precinct, nestled inside an icy crater that has bountiful resources for water. Because the Lyot crater is so far away from the rest of the precincts, we are building another crater colony at Mars Crater, number 4 on the map, as a pit stop or connecting precinct to Lyot crater. This is for safety reasons and to keep Malacandra unified without any one precinct feeling isolated. The 6th precinct will be at the base of the extinct volcano Olympus Mons. This is the tallest mountain in our solar system. We plan to have lots of tourist attractions for the explorers who trek out here, like mountain climbing and spectacular views of the expansive red rocky terrain of Mars from the peak of Olympus Mons. There are 4 plans for 4 more precincts on the other side of Mars that will complete the 10 precincts of Malacandra, the first city on Mars. Malacandra, however, needs more than a large-scale city design to run smoothly, but detailed technological developments too.
So the first thing that we need to cover is the basics of how we live, our life support systems. As we develop these life support systems, there are some important differences between Mars and Earth that we need to keep in mind. Mars is about 1/3 the mass of Earth, meaning that the gravity is 1/3 as strong. There's a massive difference in atmosphere, both in how thick the atmosphere is and in the composition. Mars's atmosphere is much thinner and composed of mostly carbon dioxide instead of nitrogen and oxygen. Being further from the sun, Mars is significantly colder and takes longer to orbit. Because of these differences, systems that allow us to breathe, drink, and survive are necessary. The primary focus when we landed on Mars was to create water and oxygen before our supply ran out. Most of our water comes from the Martian regolith, with a small amount from the atmosphere. Even before we came to Mars, we knew there was a significant amount of water held in subsurface water ice. Landing in the base of Valles Marineris, where there was likely flowing water in the past, put us in a great place. And while we've had to work hard for our water, we are grateful to not be lacking in this area. To extract water from the regolith, we use a rototiller to bring up a fresh supply of fresh soil to the surface. Radiative heating is then used to bake off water from the soil as a fan blows the Martian atmosphere through an enclosure to collect the extracted water. For atmospheric water extraction, we use Waver, or water vapor adsorption reactor. Waver works by placing an adsorbent such as zeolite in open air and then heating the zeolite in a contained space so any absorbed water evaporates and is extracted. This will only produce a small amount of water, but with limited resources, any water is non-negligible. So let's talk about just how much water we have to harvest. We need about 2 to 3 kilograms of water per person on a daily basis. However, a lot of that can come from our food. Additional water is needed for our greenhouses as well as cooling and heating systems, keeping air humidity levels normal, materials production, etc. Taking all that into account, 20 kilograms is needed per person daily. We have about a 50% recycling rate, and our Martian rovers, created from 3D printers, replenish our water supply every day. A lot of people were concerned that the amount of oxygen available on Mars would not be enough. Surprisingly, even though the atmosphere is 100 times thinner than Earth's, there is more than enough oxygen wrapped up in carbon dioxide. Even with our target of 1 million people, there will be more oxygen per capita on Mars than there is on Earth. So our habitats have enough oxygen that our colonists can walk freely without need for a spacesuit. Even though Earth's atmosphere is mostly nitrogen with about 21% oxygen, we know that we did not need the exact ratios of Earth. For example, Skylab had a lot more oxygen than nitrogen. And while oxygen can be produced through electrolysis of water, we did not want to go through our water supply in order to create oxygen. So to supply the oxygen, we primarily use MOXIE, which stands for Mars In Situ Resource Utilization Experiment. This converts Mars's atmosphere to oxygen. We have converted the MOXIE units to be much larger than they were 20 years ago to support our oxygen needs. They were originally flown and tested on the Perseverance rover, which landed in 2021. MOXIE proved to be quite successful on Perseverance. These instruments are positioned on the edge of our habitats so that the carbon monoxide is expelled into the atmosphere. Another supplemental source of oxygen is the presence of plants in our habitats. We have walls just covered in plants, and seeing the green growth is good for our moods and our lungs. We've discovered that these plants contribute up to 10% of our oxygen needs.
In addition to air and water, we also need food to survive on Mars. When we first arrived, we relied on dehydrated foods that we had brought from Earth. However, in a pursuit of sustainability, we quickly needed to build greenhouses. After considering the dietary needs of each Malacandrian, we discovered that we needed about 50,000 square meters for 2,000 people. This is the equivalent to about 9 American football fields. Running these spaces is made more efficient by the composition of the Martian atmosphere. The Martian atmosphere has about 3 times the CO2 concentration as Earth's atmosphere. Because plants thrive in high CO2 environments, we have been able to pump outside air directly to the greenhouses. This has saved both on our MOXIE usage and has caused our crops to thrive. And you might ask what kind of crops we grow. We've chosen many of our crops based on their multi-purpose features. We grow rice, tomatoes, cauliflower, spinach, various herbs, sugarcane, legumes, potatoes, and berries. Note that these greenhouses use an aquaponic model, which creates an ecosystem of plants and fish. The fish give the plants extra nutrients, and the plants filter the water for the fish. These fish are also a source of protein and have been chosen for their tastiness. So we've chosen fish such as tilapia, catfish, and barramundi. In the future, we plan to add to our protein levels by creating meat in a lab and have planned a Noah's Ark trip of a spaceship full of livestock, eggs, and dairy.
The next thing we need to talk about is the power to power all of these different systems. So based on our calculations from people's food consumptions, life support, and work needs, we estimated that we needed to produce power at about the rate of 35 kWEs per person. We decided to draw power from several sources, with nuclear power being the majority, followed by solar. We're currently working on how to harness wind, geothermal, and human motion power sources as well. So we had several options for power supplies and 2 options for the placements. We were deciding between placing the power plant under or adjacent to the settlement to minimize the amount of heat that was wasted. We decided to construct it next to the settlement due to construction cost and time. A future option is to place a power generator near ice to harvest more water. But this is secondary because maintaining the habitat is our primary concern at this point in our history. The less distance the main power supply has to travel, the more efficient the power consumption is. We can go to the next slide. Another thing we have to consider is radiation. This is obviously one of the biggest issues with going to Mars. Actually, quite possibly the greatest threat to the safety of humans on Mars. And because of this, it's important that we use highly protective material available for spacesuits, the ship, and our habitats. Without protective materials, our radiation dose on a one-way trip to Mars is about 300 MSV, which is about 15 times the maximum radiation limit for a nuclear power plant worker for 1 year, which is quite high. You can go to the next slide. So there are two major reasons that radiation is so much worse on Mars, and one, that there's no magnetosphere, and two, that there's very little atmosphere. So the Earth's magnetosphere, or its magnetic shield, blocks a lot of the radiation from hitting Earth. And Earth also has a dense atmosphere that reduces the surface radiation. Since Mars does not have a magnetosphere or a strong atmosphere, we created an artificial magnetic shield around our ship to provide some shielding from radiation. We even used this in the early days on the surface of Mars. To further limit our unprotected time, we rely on robots and artificial intelligence to do most of our operation in the unprotected areas. Eventually, we do hope to terraform the planet, but this is still a long way off and requires significant changes to the atmosphere that we have not made yet. We are able to lower our radiation exposure by using protective materials and living at a lower elevation, thus one of the reasons for choosing Valles Marineris. Thanks to research by NASA and other space organizations, we use materials such as G2O3 in our equipment to reduce our radiation dose.
To eliminate as much transit weight as possible when moving from Earth to Mars, most of the necessary construction materials for the physical construction of our habitats are generated on Mars itself. Thankfully, Mars offers a plethora of minerals in its soil composition. The primary materials used to build our structures are aluminum, plastics, and concrete. These materials are found in Martian soil, like aluminum, or are made from 3D printers, like concrete and plastics, by using Martian soil and polymers brought back from Earth. For concrete, we use a sulfur concrete developed by researchers back on Earth that is a mixture of sulfur and Martian regolith. That is the little picture of the gold-looking brick at the top of the screen. We use 3D printed polycarbonate plastics, or PC, to cover exposed sulfur concrete to protect it and block the smell. It isn't quite the same as the PC back on Earth, but it is a strong, heat-resistant, and durable thermoplastic material that we need. Our habitats rely mainly on reinforced concrete with interiors of recyclable, thermally stable plastics that can be manufactured on Mars. Each habitat has a thin water tank located beneath the roof. This and a lining of high-density polyethylene, HDPE, or a similar plastic around the walls acts as a passive radiation shield. Sleeping areas are located at the center of most homes, so they are further protected from cosmic radiation. Most of the building designs rely on spherical, elliptical, or cylindrical sections to compensate for the pressure difference between the atmosphere and the habitats. The city's industrial buildings are also pressurized but have less shielding, as the majority of industrial processes, like materials processing, manufacturing, assembly, are automated and use robots and artificial intelligence. These buildings will have a single above-ground story and 2 to 3 underground stories. The upper story will contain common areas with large aquaponic gardens that will provide workers a refreshing green space with a wide variety of plants and act as an additional radiation shield. There will be a large open communal spaces on the floor of the canyon. These will be housed under geodesic domes with reinforced concrete foundations. The diameter of these domes will be 50 meters or less, and a large terrace garden will line the inside of each dome, providing protection from radiation for the outer edge of the enclosed space, similar to Richard Heidman's design on Planete Mars. A hard plastic outer dome serves as a UV radiation shield, and an inner pressurized dome houses the plants. Both domes are translucent to allow the transmission of visible light. The inner dome is made of ETFE or some similar material that is strong and resilient even in extreme temperatures. Habitats and some common areas are built into the side of Valles Marineris to help with radiation and pressure, with a small area exposed to the canyon for some natural light. This specific location of Melachondra is located on a geographical feature of Valles Marineris that is staircase-shaped. There are roughly 3 distinct shelves, each about 1 to 2 kilometers apart in altitude. This is the original city design for A-XII. Our precinct has since grown, but the general layout has remained the same. This image is not the exact location, but it is in Valles Marineris and represents a terrace-style design used in the settlement. The 2 images in the top right are Richard Heidman's design for a dome with garden terrace, which represents common areas, and underneath that, a potential design for concrete habitats built into the side of Valles Marineris by Gus Westerman. Since our habitats are closed systems for the time being, and the atmosphere on Mars is not as complex or developed as Earth's, respiratory outbreaks are a concern, especially after the COVID-19 pandemic back in 2020. Extra filtration and air cleaning devices are used here as a precautionary measure. We use a combination of techniques. Primarily, pleated air filters are used in the air ducts with a MERV rating of at least 8 to filter out particles with a diameter as small as 3 micrometers, like mold, dead skin cell, and similar particles. These large air ducts are about 1 meter by 1 meter wide. The secondary air cleaning device that is used is an upper room germicidal light system where shortwave UV, about 245 nanometer, uses light to illuminate the top 1 foot area of the room to inactivate respiratory viruses like COVID-19. These are installed in rooms with higher densities of people, like rec centers or office spaces, in order to keep the respiratory transmission of viruses lower.
So while we've been talking about our building materials, let's also talk about how we steward those materials in our environment. A lot of what we would call junk here on Earth is eliminated because of the high shipping cost to Mars. With this low import capacity, we have a special opportunity to be highly selective about which materials we do use on Mars. Emma spoke about biodegradable plastics. One such is polylactic acid, or PLA, is a special plastic made primarily from plants, such as tapioca, and is used for 3D printing. When reinforced, it works well for dishes, toys, and other convenience items. For construction of sturdier items, such as furniture, we use polycarbonates. In addition to the plastic, we utilize fibrous plants. One such plant is sisal, which doesn't require much water, and its fibers can be used as reinforcement for certain polymers. The rest of the plant can be used in fertilizer, medicine, or fuel. By using these biodegradable materials, we can contribute to the compost in our greenhouses. There's a specific facility near the greenhouses that provides the optimal temperatures and moistures for efficient composting. To ensure that the new soil is safe for the greenhouses, we have regulations in place regarding human waste and methods of testing the soil when the composting is complete. However, no matter how well we limit it, there will always be some waste. A trash compaction and processing system, or TCPS, is here pictured. It's similar to that seen in the Disney Pixar film WALL-E. These trash blocks are converted into heat energy, which give back to our community. We've spoken about the systems supporting our community. Now I'm going to share a bit about the community itself. Psychological research suggests that one of the greatest indicators of happiness is healthy relationships. Life is meant to be lived together, and social activities play an important role in developing Melachondrian life by buoying our mental health and building a sense of unity. We are providing for that need by creating spaces for community to take place. Our geodomes house larger games and events, including the first Martian Olympics that took place a few years ago. Communal areas have also become popular spots for classes, workshops, and artistic displays. These are often seen in the shows that we stream from Melachondra. Outdoor activities are also popular: dune surfing, rock climbing, and hiking. But there's a chance to be physically active inside too. Our rec centers are all equipped with VR equipment to make workout more engaging. That being said, we want our interactions not only to benefit ourselves, but also give back to the environment. Rachel talked about human motion. We are working on gyms that solely run off self-generated power. We're also working on sidewalks and bikes that generate electricity. Finally, our events have really brought us together as a community. Holidays such as the first birthday on Mars, the Olympic Games, or an arrival of a new ship and the following welcome center all bring us closer together. These events have formed our culture, and we look forward to how it will continue to be developed by future generations.
We can't hear whoever is currently up. I think you're still on mute.
Sorry about that.
She's coughing.
A little bit of a coughing fit there. Okay. The goal of education on Mars, excuse me.
Do you want me to take over for a second, Rachel?
I think yeah, go for it.
Okay. The goal of education on Mars is not just intellectual training, but also physical training. It's a very physical experience with us living on Mars. So we've designed our education system to be 3 different phases. And in each subsequent phase, the individual is getting more and more work experience. So we call our ages on Mars Mage, standing for Mars age instead of Earth age. And we start at Mage of 3, which is about an Earth age of 6. In this first phase, we just learn basics such as reading, writing, arithmetic, etc. But then by the time that we're Mage of 8 or Earth age of 15, we start doing some internships or job shadowing. So during that phase, we will do 2 months in school and then 1 month job shadowing. This means that over the course of 1 Martian year, 7 trades are explored. In the final phase of education, we actually get to focus in on 4 different internships and really figure out what our strengths are and what areas of Martian life we want to plug into full time. So during this time, we spend 3 months at a time in those internships and then do school for 3 months. Between phases, we have extensive holidays and celebrations, along with skills testing and personality testing in order to understand ourselves and each other better. Throughout our daily schedule in school, not only are we learning, but we try to incorporate a lot of physical activity. So we have walking desks, we have bouncing chairs, and then throughout the day, we will take several breaks where we are involved in mental health sessions or physical exercise.
Okay. We also do emphasize healthcare a lot because we recognize that Mars has a lot of unique challenges. Several people were concerned about our ability to cope with the long trip to Mars and the physical changes that Mars would have on us. And this is definitely a real concern. We have increased radiation and decreased gravity. We've got bone loss and immune system alterations. We have mental health challenges and space adaptation syndrome. So how are we going to conquer all these? We have to do it together. And we really recognized that we could not do it by isolating ourselves. So it's vital that everyone holds each other accountable to their mental and physical health. So the healthcare is a public endeavor, and therefore healthcare is a public service as well. Before we left Earth, we went through the astronaut training with heightened mental health training. We learned to work together as a team, and our physical health habits were monitored very closely. Now that we're on Mars, everyone sees a medical professional once a month for a physical and mental health check. We also monitor how our bodies have changed since coming to Mars, and we do this in monthly appointments and wear a smartwatch that monitors our vitals. Some exciting Martian products are proteins and crystals that help combat and heal Parkinson's and Alzheimer's and contribute to Earth's health market.
Some of the social branches that we've talked about, such as healthcare education, need management. In order to keep the peace, maintain public utilities and spaces, and allow for the growth of civilization, we needed a form of government. The governmental model had to prepare for the rapidly changing nature of Malacandra. In the beginning, it took a more regimented style of government to ensure that all necessary tasks would be effectively completed. This was for the safety of the population. However, in this style of government, power is open to abuse. To prevent against this, the basic outline of a more democratic government was also formulated for Malacandra. In acknowledgement of when Mars becomes more independent from Earth and more self-sustainable. We have recently transitioned from this first settler stage to the established stage of government. Let's get into a bit more detail. The Board of Directors is a forum on Earth designed to help establish civilization on Mars. This board helped organize the initial wave of settlers to Mars and considers the interests of initial investors. The mission director is an elected member of Malacandra who mediates between Malacandra and the Board of Directors on Earth, informing the board of proceedings on Mars and advocating for the colony's needs. This missions director also conducts the democratic colony meetings. Malacandrans are able to discuss needs, address systemic issues, and advocate for procedural change. As Malacandra has grown, 3 sectors have emerged that have brought organization to these meetings: the necessity, the dispute, and the development, dispute management and development sector.
So all 3 of these branches work to enable the role of the government, which is 1, to keep the peace through court systems and police, make decisions that affect safety, growth of the community, such as urban planning and stockpiling resources in an emergency, and maintain public health facilities like roads, utilities, and the spaceport. And finally, some economic involvement, such as prohibiting monopolies and enforcing health and safety regulations. So the necessity branch focuses on the life support systems and ensures the functionality of current systems. The dispute management branch handles arguments and disagreements between individuals and groups. So for individual disputes, this branch is involved where a mediator is needed. And for larger disputes, this branch might make crucial decisions concerning the best course of action, such as which project should we prioritize or something like that. And the development branch is responsible for guiding the innovation on Mars through engineering projects and research emphases. So the stress of living on Mars leads to high innovation, but the resources are definitely limited. So this branch decides the best way to use these limited resources that we have. The next stage that we'll move into as our city grows is the established stage. And so the branches of the government are similar with the dispute branch becoming the fundamental sector. So the main difference here is that these branches are more systematized than the settler stage. So when Malacandra is fully established, the individual workers will be more specialized in each of their careers. The goal of having everyone involved in the government to an extent is to reduce isolation of each sector. That way, the healthcare workers must think about what the lawyers and those working for unity also are thinking about. The government's goal here is to enable a unified society that promotes innovation through interdisciplinary work.
All right, let's talk about money. Now that we're 20 years into our residency on Mars, we have more and more exports and are on a good trajectory to becoming financially independent, which we're quite excited about. But first, let's go back so we can brief you on our early funding. A fund was originally established on Earth to provide the initial money. $50 billion was raised, 60% of which was from private individual investors. The other 40% was from governments and space agencies, both private and public, mostly NASA, ESA, and SpaceX, with smaller contributions from others. This investment, however, was unique in that it did not gain immediate returns, but was rather seen as a donation for furthering human presence in the solar system. Initial flights and supplies were paid for out of this fund, as well as the salaries of settlers who came to Mars before the economy was developed enough to support salaries.
So this meaningful work that has been taking place on Mars is resulting in exports that have been profiting our economy. Our physical exports back to Earth at this time are limited because of the payload cost, but they do include meteorites found on the surface of Mars, Malacandrian jewelry and art, prototypes for new technology that have been developed, and some pharmaceuticals. Since the chemical makeup of Mars is different from Earth, some pharmaceutical materials are more readily available here. Although our physical exports are limited, we have discovered a host of other ways to engage in trade with Earth and boost our economy. A pleasant surprise is how much technology we have been able to sell back to Earth. Many of our innovations in automation and energy efficiency have come from our young workers. As Professor Erskine was saying, because of our unique education system, students have had multiple experiences in internships while still in school. The result is a much more experienced workforce. We are in the middle of establishing a large information processing system, similar to the one here and similar to many cloud processing services on Earth. Individuals or businesses from Earth and Mars will be able to purchase cloud space for significant jobs. A cloud processor on Mars is ideal because the temperatures are lower and thus our system can run more efficiently and economically. In addition, the heat waste from the system will supplement the heating of Malacandrian city-states. The processing centers will be located below the habitats, businesses, and other enclosed spaces, allowing the heat to vent upward. As Professor Erskine said, some exports don't come in the form of physical objects, but they do come in the form of connections. Mars offers a unique cultural connection to Earth. Many of us living here create video journal entries, and some wear high-res cameras around to collect footage that is later edited and broadcasted back to Earth by a major network. Research opportunities on Mars are driving our excitement for exploration. One of the space connections I'm most excited about is Space Station M. When it is finished, it will serve as a one-stop station for spacecraft going further in the solar system. Spacecraft will be able to take advantage of the Lagrange points to enter and exit orbit with minimal fuel usage. As the future spacecraft stock up on fuel and provisions before going beyond. In the future, as Malacandria expands to 1 million people and new precincts are established, trade will undoubtedly occur amongst the precincts. Pictured here is a map of our planned precincts. For example, Wyatt Crater, number 5, is rich in water. Gale Crater, number 8, looks to have an abundance of titanium, but a lack of water. This could result in possible trading partners. We are also working on our tourism, which likely won't debut for a number of years, but eventually Mars will be the travel destination for vacation, with most tourists taking 26 months to go on a year-long Martian adventure. Travelers will be able to choose multiple locations to visit by using Space Station M as a layover between intra-Martian travel. Points to note are the highest mountain, Olympus Mons, and the largest valley, Valles Marineris, in the entire solar system. Finally, another export we are developing is education. Malacandria University offers an array of 26-month elite master's programs. Our university isn't quite so green and lush as the campus pictured here, which you might recognize, but it will have its own beauty, sweeping landscape and starry skies. Most sciences are covered: geology, physics, engineering, astronomy, chemistry, and many others. However, you can also get an MA in leadership, or specifically outdoor leadership, humanitarian and disaster relief, city-state design, or business with a focus on interplanetary trade. On the 7-month journey from Earth to Mars, classes are taught by experts and preparation is given for their year on Mars. The skills learned both in traveling to and from Mars, as well as living on Mars, add so much more to a master's degree than a class on Earth can. The cost of this program will start at $175,000, but depending on the program goes up to $275,000. Because of the steep price, many large corporations, governments, the UN, and space agencies will likely sponsor students. Organizations can also sponsor employees to go through an intensive year-long leadership workshop on Mars. Again, a 26-month endeavor, using the 7 months in transit there and back for remote work. This leadership training will also be offered on Earth as online classes run by Malacandrians. But the real adventure is in the space travel. We hope that you will join us on Mars one day soon. We think you'd like it here. But whether or not this is for you, we hope this talk has given some insight into the possibilities that await just one planet away.
Wonderful. That concludes our presentation. We hope that this was a bit of an escape on your Tuesday evening and that you enjoyed our vision for what life could look like on Mars. So now I invite you to come back to the year 2021. We'll leave 2050 for the future, and we'll have a time of Q&A. I believe that Jim is going to ask us questions if any questions have come in. Please feel free to ask any questions about, the technical aspects or any kind of dreaming that we did about our Martian settlement.
So we don't have any questions. I personally have a question though. Do you see a system of bartering being some of the first form of compensation for trading products, or do you see a monetary system being created right away?
Yeah, so we designed our system so that there was a very structured monetary system. We worked with the fiat, the currency fiat, and have that system connected very much to Earth for decades. So even by 2050, we have only the Martian economy just starting to kind of get independent at that point. And the reason is because we designed our system with a pretty close tie to Earth and to this board of directors on Earth that would help Martians make decisions for the first few decades. Anything else to add?
I might mention also that in the very first 12 settlers, or that first generation, would not so much need currency. That was brought in after some of the more immediate concerns were taken care of. But as Professor Erskine said, it was something that was we imagine it would be something that would be very structured.
Okay, I'm kind of shocked that we don't have any questions coming in. I don't know if we're having issues with our Facebook feed or not, but
I'm seeing a few here.
Oh, maybe maybe my feed's not refreshing. Oh yeah, sorry about that. What would population growth by immigration from Earth, would population growth by immigration from Earth, procreation by original colonists, or both? So how would the population increase on Mars?
Yeah, we had kind of said that it would be both. Obviously, at first, it would be primarily from ships from Earth, just because there aren't many people on Earth. But we mentioned that our first kid was born on Mars in 2036. And so there is starting to be some kids who are just born on Mars right there. But by 2050, for sure, a lot of that growth is still from immigration.
Yeah, and part of that reason is so that we can we plan on, only being on Mars ourselves for about 5 years before children are born on Mars. And there will be a lot of biological testing in those years before real Martian children are had.
Mary asks, how long did it take you guys to come up with this entire concept?
We started working on this project back in June of 2020. It was kind of like an opportunity for us students to do because some people had internships for physics or engineering that kind of fell through because of COVID. And so this was kind of an option for us to do instead that would provide, something nice for your resume and just something fun to do as well, something lighthearted and fun to think about, fun to talk about. We had so much fun in our meetings talking about not just the engineering and physics side of all of this, but also the social, economic, government, everything. So it definitely took about a month for us to do the entire report. And then when we did a presentation for our college in the fall, we took about another month once we got back to campus to complete this entire presentation. So I would say about 2 months, 2 to 3 months of work total.
Yeah, I was going to say the same, Emma. I think it was about a month of complete brainstorming and research, and then about a month of like writing and creating a presentation.
So what kind of, so you mentioned at one point there would be some sort of police presence. What kind of police and or military do you expect you would need, and would they be armed?
To be honest, we didn't get that far into exactly what the military would look like. I think the level of armedness of the police force or the military would have to adapt to how people who came to Mars were armed, and what sort of products were created on Mars. So, I mean, if you're starting to get heavy weaponry developed on Mars, either in people's free time or a black market or whatever, you're going to need to have some more arms there. But I think we wanted it to kind of just adapt as needed, and not initially create a very heavily armed militia or anything like that.
Yeah, I'd also jump on that and note that the people who are coming to Mars have been through psychological training and kind of character building as a team before they come out to Mars, which obviously is not going to solve all problems, but we hope that it will limit some of the more societal conflict, would limit some of that societal conflict.
For this presentation, did the group examine the current closed systems testing being conducted on Earth for lessons learned?
Yeah, I'm wondering if the person asking the question is wondering about these Mars simulations that occur in, I think Devon Island has one station, and then there's another in a desert in the US, Mars Desert Research Station. Yes, I have actually friends who are involved in those experiments and have studied the reports extensively. It's fascinating. These are actually happening around the world as well. It's fascinating how different the individual studies are. So some are very successful, how well the people get along and work, and some actually have to end early because they're so unsuccessful. So it's all over the board how those personnel experiments work out.
Considering the gravity differential for muscle and bone density management, is the treatment more nutrient based or physical, or with physical weights similar to treadmill run and exercises done on the ISS?
It's a little bit of a combination of both. I think we would put more emphasis on the physical exercise and weights. In our education system, we're incorporating a lot of physical activity into just the day-to-day life and developing these habits that hopefully people will continue as they get older. But yeah, really encouraging a lot of that physical activity.
Do you foresee population being limited in the event of colonizing Mars? Would there be a point where you would want to restrict immigration?
That question seems so far off at this point that, I mean, even if you listen to Elon Musk talk about his plans to, he not only wants permanent human presence on Mars, he wants to terraform Mars. So he wants to make Mars considerably more livable than it is. But his big goal is to make Mars a very attractive place. The work there will be meaningful at first, so he believes that will attract a lot of people to it. So I think the first question is, can we get thousands or maybe 1 million people wanting to live on Mars? And then perhaps the question will be, how do we keep people away?
Okay, so this is a long question, so this just came in by email. Has your team considered Martian science as a possible market? We are still in the early centuries of exploring the planet, and there will continue to be a large number of scientists on Earth with interests in investigating the geology and environment of Mars. At present, there are government and private agencies on our planet willing to pay for data about this. I see no reason why this shouldn't continue to be true. So could support for scientific studies be a source of income, gathering specimens, collaborating with visitors or off-Mars scientists undertaking long-term regional studies?
For sure. I think that's a brilliant way to connect Earth and Mars in a partnership towards research and to boost Mars' economy. Also, I think that's kind of what the whole idea of a Malacandran University is trying to encourage. It's trying to get future researchers who are going back to Earth to get interested in life on Mars and all of the science and technology discoveries that are happening there.
Okay, with the wide variation of the success or failure in those isolation experiments, it has helped. Oh, sorry, this is following up with the isolation experiments question earlier. With the wide variation of success or failure in those isolation experiments, it is helping redefine the psychological profile that Emma mentioned. So that wasn't a question, that was just a comment. Give me one more second to see if we have any more. Do you consider aspects of using Mars colony to be a jumping off point for further solar system exploration due to the position of Mars and reduced gravity?
For sure. I think that's what's exciting about the Space Station M that we talked about. So that would actually be used as a refueling and restocking spot for people or equipment that would make its way further out into the solar system.
Okay, I think that is all our questions. Give me one more second to refresh and see if we got any more. Oh, how long before the first telescope is built? With Mars' thinner atmosphere, it should be a great place for ground-based telescopes.
Yeah, and not only that, but it will be really fun to observe meteor showers. So my area of expertise is the meteorite environment, specifically as it pertains to spacecraft risk and operations. But meteor showers on Earth are our own earthly meteor showers. So there will be different meteor showers on Mars, and Mars does have enough of an atmosphere to create shooting stars for little particles to burn up. And so it will be fun to observe not only the universe with telescopes, but to see what new meteor showers will be on Mars.
Most missions to outer planets use gravity assist to get going faster. They would not be stopping at Mars. Oh, again, just a comment, I guess. Okay, I think that is all the questions that we have. Probably 20 more will. Oh wait. How close? Oh, sorry. How close were your ideas to other groups that submitted this?
Yeah, it was kind of all over the map. A lot of the technical details, so like Waver and Moxie creating oxygen and water, that's technology that is being developed right now and is actually being tested on Perseverance. Moxie is on Perseverance right now. So a lot of the technical aspects were similar between reports, and then they differed more in social, cultural, governmental, even what types of questions people addressed. The design that won was actually an open source forum. I believe they started on Reddit. I might have to correct myself there, but it was actually contributions from, I believe, 80 people to this design. And you can find it online if you just Google the Mars Society Martian Settlement Design Contest.
Okay. I think now that was our last question. So thank you very much. Drew, if you're there, we'll let you pick back up. And again, thank you all for presenting tonight.
Yeah, thank you so much for having us this evening. It's wonderful to spend the evening with you. And yeah, thank you again.
All right. Well, thank you very much to the entire team for a very interesting program. We're going to do our abbreviated business session here. When we're online, we cut back and we just have any reports that any of our officers have submitted to our secretary, Kathy. And Kathy, if you're there, I'll give you the floor to pass things along.
Yes, it's going to be nice and short today. We are forming a planning committee to work on the 2024 solar eclipse. If you would like to participate in this committee, please email eclipse@naperastro.org. And that is all I have for today.
Okay, thank you, Kathy. I'll click on the screen there. So we're ready to wrap up. Again, thank you all for joining us this evening. I hope you've had your minds stimulated and thinking spacey things. For members, we have our after socializing on Zoom, and in just a few minutes, when we've closed this program or this meeting out, we will start up that one for socializing at, and it's the same meeting number that we've used in the past for that. It was in your newsletter and it's on the screen now. So otherwise, I'd like to say good night to everybody. And again, thank you for joining us. And I hope that you can visit with us again in the future. And again, if you're watching us on YouTube, subscribe. All right, good night, everybody. Have a good one.